All right. Thank you, Andreas, for introducing us and the audience to the capabilities of the Jülich supercomputer. I would now like to provide a brief outline of the agenda for today. Pouya from the Nickel engineering team would cover motivations for high-performance GPU-centric communication in AI and HPC workloads, followed by a brief introduction to Nickel, its API, its capabilities, and a set of labs that are covering a basic Hello World application and a real-life HPC workload like a Jacobi solver application. Subsequently, Benjamin from the NVSHMEM engineering team would cover the introduction to NVSHMEM, its APIs, its capabilities, and a set of labs covering NVSHMEM Hello World and the same Jacobi solver, but implemented using NVSHMEM's communication APIs. Finally, I would be introducing new features in both Nickel and NVSHMEM, Nickel 227 and NVSHMEM 3.3 release, specifically symmetric kernels and Python bindings, and conclude the presentation with a little preview to the GPU communications libraries roadmap. I would now like to hand over to Pouya to get us started. Over to you, Pouya.
All right. Let's start here by our motivation and goal. As you know, emerging HPC and cloud service providers are adopting GPUs to support computational power required by modern HPC applications like AI. On the right side, you can see the top 500 share of the accelerators, and you can see NVIDIA GPU shares. NVIDIA GPU shares are there, and they have few percentages there. As part of having these GPUs deployed in top 500 supercomputers, it's important and critical to also have efficient and scalable GPU to GPU communication. And this fast GPU to GPU data transfer builds on top of technologies like PCIe, NVLink, RDMA, that is like InfiniBand or Rocky. And you can see, for example, another graph on the bottom that shows the share of interconnect family for the top 500 systems. There are multiple use cases for having efficient data transfer among GPUs. Some common ones are distributed deep learning, like for both training and inference. It's for large-scale simulations and scientific computing, and also for real-time data analytics. So as part of today, in order to learn about how to have fast and scalable GPU to GPU communication, you will learn about two of NVIDIA's solutions for GPU to GPU communication. Nickel, which is for low latency and high throughput GPU to GPU communication. It uses two-side paradigm. And then NVSHMEM, which is for finer-grained GPU-centric communication that enables you to have one-sided communication. Okay, so now go over the introduction to Nickel. So it's an NVIDIA collective communication library. It's designed based on the communication patterns originally from AI applications, and it supports both single and across multiple nodes for GPU to GPU communication. It supports also point-to-point and collective operations like all reduce and broadcast. And one thing that separates it from other communication libraries is the library is running on the GPU. So the communications calls are translated to a GPU kernel, basically on a CUDA stream. There are some links on the bottom for you to learn more about Nickel. As part of the presentation today, we would cover low latency symmetric kernels that was released as part of Nickel 2.27, and that would be in lab 5. Okay. So here we would cover some basic examples of Nickel to get you a sense of what APIs it provides. Next slide, please. So in this slide, I'm talking about Nickel APIs that are used for communication. Like MPI, we have two sets of point-to-point and also collective operation. The signatures are similar for these APIs, with the difference that you can pass a CUDA stream to these. You can see, for example, all reduce example, the picture on the bottom. It's a collective operation where each rank has its own data, and then you choose an operation to reduce all this data reduce all this data and then broadcast it to all the participant ranks. These APIs will be used later as part of the labs for you to write some codes. Another part of Nickel API is about having initialization and teardown of the Nickel communicator. The graph on the right side shows you the flow. So first you need to create a Nickel unique ID that you will use it later in to generate the communicator. One rank creates this ID and then uses uses out of band broadcast to give it to all the other participating ranks as part of the communicator. And you should only call this once, so just one rank should call it. Then we have an object of nickel.com that you can use, and each rank uses it to registers itself, initialize a nickel.com in its rank for to be a part of the communicator. And then there are some communication happen by the API as I showed you on the previous slide. And finally, we have the nickel.com destroy. Next, in this slide, I want to show you how to use some of the APIs that we just covered 2 slides ago. So the first step is for you to create a stream. As I mentioned, Nickel is a stream ever. So each rank creates a stream, and then depending on in this example here, we have a simple send receive. So depending on the rank ID, which is if it's rank 0, you would call Nickel send to send n chunks of data to rank 1. And then on the rank 1, if we have that check to receive that amount of data. Finally, we do a CUDA stream synchronize to make sure that the streams have finished their work and proceed to the destroying the Nickel communicator. As part of Nickel APIs, there are blocking. So send receives are blocking in order to make sure that you are not having a deadlock, and also to schedule them on the streams more efficiently. Nickel has a concept of group start and group end. The way to use them, it's outlined on the right side. So you basically wrap your Nickel APIs for communication around Nickel group start and group end. That way you would get more performance, and the operations will be fused and executed back to back on GPU streams. So I think this is time to get our hands dirty. Go to lab 1. In general, if you would like to use Nickel library, you have to include nickel.h in your file, and then you are able to compile it by passing -l Nickel. We have made this easy for you if you go to the Supercomputer Center and now open lab 1. So if you have to go to you have to synchronize your JSC material sync. And then there is a HotEye folder on your home directory, and you can go to Nickel and lab 1 and look at the Nickel basic application here. We would like you to give this a try to make sure you can run things smoothly. There is nothing for you to fill in here. Just take a look and execute it. You can build it by running make build, and if you want to run the application, you can just do it make run. Again, this is a chance that we are the engineers of Nickel. We would like to go over as much as material we want and write code together. So if you have any questions, please shoot us on a Slack if you're facing anything. Okay, I'll wait for 5 to 10 minutes so everyone can catch up on this one.
While we wait, are there any questions on Slack that you're seeing, Ben, that we need to address?
No, mostly there's environment questions that Andreas is helping. Thank you, Andreas.
Thank you, Andreas. So this first lab, as Pouya was talking about, will go over the initialization of the communicator, sending and receiving the data. So it's a very simple Hello World application like we saw on the slides. If at any point of time you don't see it working correctly, you have issues with the output, just put a snapshot on Slack and we can take a look and see what's going on.
There's one question, I think it's a good one for Pouya to answer for everyone. So the question is the code shown the same running on all GPUs? How do we make sure they all start together? How is the nickel UID shared out of band?
So yeah, that's a good question. We use MPI right now to MPI broadcast to if you look at the file to broadcast that ID. When you have that nickel init communicator, then it makes sure that the GPUs run all together. But most importantly here, you don't need to usually worry about that if you're using nickel group start and group end. So that would help you not run into deadlocks.
To add just to specifically answer the first part of the question, yes, the same code is running on all the GPUs. So it's a sort of single program, multiple data style. There's a request to cover more about how you use nickel group start and group end to avoid deadlocks, specifically what that's about.
Yeah, so all you have to do on this one is like, send and receive operations are blocking, meaning like if I call send on rank 1 and there is no receive on no receive on the other rank, then I'm waiting for my operation to be completed to proceed. By using group start and group end, like we make sure that we are not, when we have multiple send receives, we don't run into a deadlock here. And you can see an example for point-to-point on this slide. Also, there is an example that shows how to do broadcast, that it's looping over like all of the participating ranks and it's sending data to each one of them.
And just to add to what Pouya just said about group start and group end, the way it works internally is that Nickel would be able to maintain an internal queue of operations to make sure that those operations are dispatched and the corresponding kernels are launched. Because if the kernel is not launched, then essentially, as Pouya said, one rank is essentially hanging for the other rank to arrive. And if that hasn't arrived, then the operation would deadlock. Also, it gives Nickel the opportunity to basically, issue back-to-back operations on the same CUDA stream. So like in the example here with broadcast, where you have multiple sends on the CUDA stream, they can be issued back-to-back, and that fusion allows to optimize for performance, especially in the low latency cases. I see a question about the print statement not being correct, 2 devices on rank 0. I believe that is because we're just emitting out the number of devices that are on the system using CUDA get device count. So it is still that you get 1 device per rank. We do that by using called CUDA set device in the lab. You'll see a code of line of that as well. But we're just querying the number of devices that CUDA can see using CUDA device get count. And that turns out to be 2 for that example.
So you see 2 devices because we ask CUDA how many GPUs there are, and you're only going to be using one of those devices for each rank. Yeah, for the person who's running make build, don't run make build, just run make. Sorry, that's a typo.
Yeah, I apologize. That's a typo on the slide. Thank you for pointing it out.
Sorry. Okay, so you're having trouble.
Oh, I know that one. I'll answer.
Okay.
Thank you, Pouya.
Pouya is going to help you on Slack. Are the nickel primitive APIs nickel receive, reduce, send, receive, copy, send, blocking or non-blocking?
I can take that question. So those are internal Nickel APIs, which are implemented in the Nickel code base. If I remember them correctly, those are APIs or device APIs as part of the Nickel code. So they would be, depending on what type of transport they're targeting, there may or may not be blocking or non-blocking. So an example of that is if you're doing communication over NVLink, that operation may be blocking in nature. If you're doing communication over a remote network, depending on if the operation is being offloaded to a NIC, that operation will be non-blocking in nature. So it really depends on what kind of network is being targeted by those internal, by those primitive APIs, which are part of the nickel code base.
All right. In the interest of time, maybe we should move on from this one.
Thank you. Thank you, Ben.
Yeah, if you have any issues, I'm on Slack. I'll try to address it.
All right. Thank you, Pouya. I'll hand it over to Ben now to introduce us to NV.
Okay, thank you, Pouya. Thank you, Arnav. Thank you, Andreas. I'm going to now introduce NVSHMEM. So NVSHMEM is another communications library that NVIDIA maintains and builds. NVSHMEM is NVIDIA's implementation of the OpenSHMEM spec standard. If you're familiar with OpenSHMEM or the lineage of Cray-SHMEM, it might mean something to you. If not, don't worry, I'm going to introduce the concepts here. So we implement and extend the OpenSHMEM API standard, and OpenSHMEM has a couple of special things. It operates with a partition global address space programming model, PGAS. I'm going to introduce that in detail on the next slide, so I'm not going to talk about it too much now. It mostly operates with one-sided semantics, so we use put get primitives instead of send receive to do data movement. What I mean by one-sided in this case is that only one process is involved in moving the data. So in Nickel, you have one process called send and the other process called receive. So the sender marshals the data, shoves it into the network, and then the receiver unmarshals it and saves it to wherever they want it. In the one-sided mode, only one side is actually doing the data movement. So it's really nice for doing things that are kind of asynchronous, and it makes it fun. We also have this shared memory heap. Again, that's related to the PGAS on the next slide. And then the thing that's really unique about NVSHMEM is how GPU-centric it is. So we have GPU-initiated communication. We support data operations where the GPU threads themselves are actually doing the data movement and putting data on the network, whether it's NVLink or a regular RDMA network. We support multiple scopes. I'll talk about those later. We support narrow data types like half and FP8, and we support tensor operands, GPU-specific AI data blocks. We also have CPU-initiated on-stream APIs that are similar in principle to the Nickel ones that Pouya was talking about before, where they work by enqueuing a kernel onto a stream. I want to just briefly talk about this picture. So the key thing to take away from the picture on the right-hand side is that the CPU is sitting idle. After it launches the kernel, the GPU kernel itself is able to do data movement by calling APIs like NVSHMEM put, and then that will result in network traffic without the CPU being involved in any way. Finally, since NVSHMEM 3.3, we have first-party language bindings for Python. There's a package called NVSHMEM for Py. Arnav is going to talk about that later. Could you move on? Thank you. So this is that PGAS picture I promised. So the important thing to think about when you're talking about a partition global address space is this concept of a symmetric heap. And what we mean by a symmetric heap is it's a sort of shared window where each GPU and each instance of the NVSHMEM runtime. So you can think of these like MPI ranks. We call them PEs in NVSHMEM. That's a legacy of the SHMEM spec. So each PE has a view into every other PE's memory space. We call that symmetric because all allocations within the symmetric heap have to have the exact same shape and size. So the interesting side effect of that is that in order to allocate memory in the symmetric heap, you actually have to do a collective. So you call NVSHMEM malloc, and every single PE in your process has to promise to call that function together. That will return you the same offset on every PE. And then because we have those size and shape and layout assumptions that are safe to make, NVSHMEM can actually use those inside its runtime to make really efficient use of the hardware. And it works really well for things like irregular data access patterns and so on. So it's really important that when you call NVSHMEM malloc, you always call it together across every PE, and you always call it with the exact same size for every PE. Just contrast that with CUDA malloc, where it returns a pointer that is only visible by one PE, and it can be any size. There's none of those same kinds of restrictions. Okay, now it's time to do a similar example to the MPI, the nickel example, excuse me. So this is an example of NVSHMEM interoperating with MPI for library initialization. The reason that we support that is a lot of existing multi-process applications use MPI already, and it's nice to provide good interoperability to give an on-ramp to using NVSHMEM. So what we're doing here is we call MPI init, we're getting our COM world out of it, and then what we want to do is use that COM world to initialize NVSHMEM. We provide this NVSHMEM init adder data structure where you can pass NVSHMEM a pointer to the MPI communicator. So that's what we're doing on in the line where you see NVSHMEM X init adder. We're telling NVSHMEM, hey, I have this MPI COM world. I want you to create an NVSHMEM global runtime with it and use the process rank mapping from MPI. So that's why it's safe to do things like assert that the number of ranks in MPI is the number of PEs in NVSHMEM, and that the rank to PE mapping is sort of identity. So it's just a really convenient way to create NVSHMEM runtimes. And then when you're done, you just tear everything down with NVSHMEM finalize. I'm going to introduce some data movement operations, although we're not going to use them quite yet. So like I said, data movement operations in NVSHMEM involve moving something from one place in the symmetric heap to another place in the symmetric heap. In this case, we're going to talk about two variants of NVSHMEM put. So the first one is NVSHMEM put on stream. The T is just a stand-in for a type. So it might be NVSHMEM X int put on stream, or NVSHMEM X float put on stream, or whatever type you want. It takes a source and a dest pointer to that type. It takes a size, which is just the size of the vector of that type. And it takes a target PE. It's a one-sided operation. So what it's going to do is just a mem copy, essentially, a distributed mem copy from source to dest, with the number of bytes will end up being the NLMs times the size of the type you pass in. There's two variants here on the screen. The first one is on stream, which means it's initiated from the host. You pass in a CUDA stream, and then it enqueues that work on the CUDA stream. The second version is declared as a CUDA device function. And what that means is that if you have a kernel that's already running, you can call that function from the device itself. So you have a kernel that kernel will call the NVSHMEM API, then that does the data movement without involving the host at all. Those functions, these device ones, have scopes. So NVSHMEM supports a thread, block, and thread, warp, and block scoped APIs. And what that means is if you call something with a scope, you as the developer promise that all threads within that scope call the API together. And what you're doing by promising that is you're telling NVSHMEM how many hardware resources it's allowed to use for that operation. So if you call NVSHMEM put block, then you're promising that every thread within that block, which is to say every thread that gets launched on the SM together at the same time, promises to call the function together, and then NVSHMEM is allowed to use that whole SM for the operation. We'll talk about that more later. We're going to do an example that brings this up, so it'll make sense later. Next slide. Oh yeah, go back one, sorry. The X in these APIs just means that they're extensions to the OpenSHMEM API. They're not in the OpenSHMEM standard. Okay, the other big family of operations that NVSHMEM has is synchronization. So today we're going to be using barrier So we have similar to the put operation, we have an on-stream version of the barrier that takes in a CUDA stream, and then we have a scoped device version of the barrier. What a barrier does is it makes sure that basically if everybody calls the barrier, the first process is to call the barrier, wait until everyone else has called it, and then it ensures that everybody's in sync. Next slide. And I see the questions coming in. I'll get back to them while the lab is happening. Okay, so to use NVSHMEM, you include NVSHMEM.h and NVSHMEMX.h. The reason there's two files is NVSHMEM.h is for the functions that are strictly part of the OpenSHMEM spec, and NVSHMEMX.h is for extensions. You can compile and link against the library -l-nvshmem. We have a file, I think it's actually been renamed. I think it's called nvshmembasic.cu if you want to look in the nvshmem/lab2 directory. And then you just, same as for the nickel example, do make and make run. We'll pause here. I will go over the questions that came in. Yeah. Okay, so what is a stream? How are thread warp block related? So a CUDA stream is a wrapper of a CUDA stream is a way to tell a CUDA device to execute work asynchronously. So you create a kernel, like a program that's going to run on the GPU SMs, and you enqueue it onto a stream, and then CUDA promises that if you put work on the same stream, it will happen in the order that you put them on the stream. How are thread warp block related? So I'm going to give you the very short answer. Thread is one element in a single instruction, multiple thread program. It's the sort of fundamental smallest thing that you program when you write a kernel. A warp is a group of threads, and a block is a group of warps. Sort of. Is NVSHMEM mainly used to have finer grained control of communication in a GPU in addition to fusing communication with computation? Yes, that is a perfect description of what NVSHMEM is meant to do. Is it possible to use APIs of both Nickel and NVSHMEM in a single application? Also, yes.
Yeah, one example of that could be that you have an all-reduce operation that you want to be able to launch between a set of GPUs, which is, let's say, doing some sort of a computation of a gem. And then you have another set of GPUs that are completely independent, and you want to use NVSHMEM to initialize those set of GPUs and launch a one-sided communication operation on. And you can mix this in both the stream-initiated or stream-aware APIs that Ben talked about and Pouya talked about, or you can do it with NVSHMEM device APIs and Nickel on-stream APIs, where the kernel is using NVSHMEM device APIs to move data, and the host side code is probably using the stream-based API to move data.
Sorry, that was an accident. I didn't mean to interrupt you.
Oh, that's okay.
Are you done, or did you have anything else to say?
No, that was it. And there's another question about NVSHMEM. Since we have put and get, will network engineers be able to make their own custom collective communication with NVSHMEM? Ben, do you want to take
Yes.
one?
The answer is a resounding yes. And that's one of the things we're really proud to have seen the community do. So if you look at projects such as DeepSeek or Perplexity's dispatch and combine kernels for mixture of experts, they found that basically the existing communication patterns that we have as sort of pre-canned as collectives didn't match exactly what they want to do. I'm not going to go into the technical details too much, but basically what they wanted is sort of close to an all-to-all, but like kind of not really. It's got some broadcast in it. So they were able to use both their own fully custom stacks, but also NVSHMEM to implement their own custom communication patterns that are not easily represented in things like prefabricated in other libraries today. So yes.
And I think there's more detail of how to implement an all-to-all using Nickel, using NVSHMEM in another talk by one of our contributors, Jeff Hammond. He presented this material about a week ago at GPU Mode. So if you want to check it out, its link is available on YouTube. We'll also attach that link later towards the end of the presentation.
Yeah, and I think these slides are being published. at some point. So you'll be able to go click on these links. There's a blocking and non-blocking put operation, but only blocking wait until operation. Well, yes, that is correct. I don't know how you would do a wait in a non-blocking way. I think wait is kind of by definition blocking. It depends on what you mean by blocking, right? So if you want to have something asynchronously wait in the back end, on the other side, you can do that, but the wherever you're actually calling the wait is not going to be able to be non-blocking. Oh, thank you. Someone sent Jeff's talk to the chat. Yeah, Jeff is a great speaker. I highly recommend watching it. Someone is having a compiler problem. Unsupported NVHPC compiler. NVC++ is the only NVHPC compiler that's supported. Are you sure you have the environment sourced correctly? Because we tested this kind of just before the session.
Yeah, you need to probably create a new terminal with a fresh sourced environment.
Thank you, Andreas. Is MPI mainly used for coordination work that cannot be done GPU to GPU through the CPUs? Often, yes. We have different people who have different needs. So MPI is really common in the HPC community, and for training. A lot of people doing inference are building custom things on top of launchers like Kubernetes, or whatever they want. Some people are even building fully custom launchers. But yeah, there needs to be an out-of-band communication stack, and MPI is really convenient, right? A lot of us HPC people just like using it, or at least know how to use it.
And to add to what Ben said about MPI's usage in NVSHMEM, at least in the example that he talked about, their MPI is a vehicle to bootstrap NVSHMEM. So NVSHMEM has a control path and a data path. The data path communication is all happening between the GPUs over networks like NVLink, InfiniBand, Rocky, some of the transport that Pouya talked about in the motivation. But the control path is all done in that example using MPI bootstrap. We also support other kinds of bootstraps, such as PMI, PMIX, OpenSHMEM, and also a TCP-based bootstrap. But we chose to just do the very simple thing right now for the purpose of this lab, which was using the MPI bootstrap and demonstrate the interoperability of NVSHMEM with MPI.
And we showed you an example of the unique ID style of bootstrap where you have to do the communication out of band in the nickel section. So it's nice to give a sort of contrasting experience. But yeah, basically, there's a lot of tools in NVSHMEM that lets you do stuff however you really want to. It's really flexible.
All right, Ben, how are we doing on time? Should we move to the next set of?
I'm not really tracking. Probably the fact that you're asking means we should move on.
Let's.
Can I summarize? Oh, real quick, this is a good question. Can I summarize what make run did? So what make run did was essentially use Slurm to launch several processes that are compatible with MPI, and then it just launches the NVSHMEM program. That's a good question about MPI. I think we'll have to get to that later in the discussion section, like after we're done presenting. It's a big question. So now I'm going to introduce the advanced example. We have a real workload that we're going to use to drive a little bit more complicated work here. We're going to use the Jacobi differential equation solver. Can you click? Yeah, great. Thank you. So for myself and for, I assume, a lot of us on this call, the first program we ever GPU accelerated was using the Jacobi method, the relaxation method to solve a differential equation. I'm not going to go into too many details, but the very basic way that works is you lay out the initial conditions of your state on a big array of memory, and you perform a repetitive sort of, they call it a relaxation, but basically you're taking local and global averages of the array. So we are going to partition the array into multiple GPUs. You've got 0, 1, 2, 3 here. And then we're going to do two interesting things. The first one is a stencil operation. It's a 2D 4-point stencil. What that means is if you're considering the purple chunk, you're going to accumulate, you're going to do a weighted accumulation of your 4 nearest neighbors, the 4 contiguous things, elements to you. And when you accumulate something out of the array, we just make sure to pad it with zeros so that the accumulation has no effect. That's why that's colored gray. So you want to click next. Yeah, so this is what that code looks like. It's doing a weighted accumulation of its neighbors. You do that process to every element. Next. Yeah. So then once you do that, because this is a distributed version of the Jacobi solver, you actually can't get away with just stenciling everybody. You have to do what's called a halo exchange. And the halo exchange is you're going to send the edges, basically wherever you accumulated from something that you don't have access to, meaning you accumulated from all those zeros. You have to actually now inform your neighbors of what they should have accumulated so that on the next iteration, they pick up the correct data. And what that looks like communication-wise is you're going to do basically a bidirectional ring. You're going to send data up to your nearest neighbor, and you're going to also send data down to your nearest neighbor. The way we're going to do that is first, Pouya is going to walk you guys through using nickel send, nickel receive to do that. And then I'm going to take you through using NVSHMEM put to do that.
All right, so you're going to look at some of more nickel advanced features in this one that you're going to use to solve the nickel Jacobi solver. As we talked, GPUs support multiple CUDA streams to run concurrent flow of operations, right? And so far, we have had no overlap of communication and computation. So here, the goal is, can we overlap the streams together and can we assign them priorities, right? And by doing so, like we are making sure that the communication streams are scheduled, and sometimes the communication needs to get higher priority, right? So in this example here, you can see like a few CUDA APIs, like CUDA device get a stream priority range that would get the priority range of the GPU as the least and as the max priority. Then in this one, when we have 2 streams now, like one is for compute, one is for just pushing, we can assign priorities to those streams. And in the next example, you're gonna get a sense of it to like do this priority assignment. So here, I'd like you to go to lab 3. Look in the code for the to-do parts. There is an unsolved version. You should open Jacobi unsolved.cpp. And we gave you a bunch of APIs. We also explained Jacobi solver, and now we also explained how to assign priorities. Just look at the code and fill in the parts that's asking for the to-do part. If you have any issues, Slack us.
Just a correction, it should not be make build. You can just do make, and by default, it will try to build the Jacobi unsolved one. It may have compile errors, obviously because certain parts of the code are missing or certain variables are unused. So please be sure to take a look at the to-dos and reason through how you would want to use the send receive APIs here.
So this is the lab that you should write some of these codes. You can use the APIs that we have provided here.
And I can bring back the Jacobi picture just so that in case people have question about the communication pattern, it's right here up in front of you as well. Ben, are we getting any questions yet?
I think people are spending some time to try and understand the program, which makes sense. We have the several people are typing, which Slack does when it can't decide how many, when it can't count.
Let me know if folks want to be able to get to the picture about the API descriptions. I can flash that back. I thought this image would be useful when you think about the problem.
Can we post the slides? I think they will be posted on the Hot Interconnects page after the presentation. I think these will be distributed.
Yeah.
I don't think we can post them before that, unfortunately. The API descriptions. Okay, he wants to see the API descriptions.
Thank you so much for asking that. I put it up there, the send receive APIs. I can explain the arguments one more time. The send API takes in a send buffer pointer, the count, which is the number of elements in the send buffer, the data type, which could be an int, U32, float, whatever the data type you describe the data in, the peer, which is the rank you want to target for communication. So for in the case of send, it's the target rank you want to send the data to. The COM object, that's the object that is returned when you do nickel com init rank, which we have talked about in the hello world example. And then the CUDA stream, which is the stream that you want to launch this nickel kernel on. It could be the compute stream or it could be its own stream. And then you have the nickel receive API, which takes in a receive buffer pointer. Again, this is the pointer to a buffer which is on CUDA memory or on GPU memory. Then count, which is the number of elements in the receive buffer. The data type, which is the type of that your data is described in. The peer, which is the rank you want to be able to receive this data from. So if you pair a send receive, then those are basically their opposite ranks. And the communicator, which essentially is the object that's returned by nickel com init rank, and then the CUDA stream.
And the question of, are GPUs physically close for the purpose of communication? Today, yes. So the way this is working is everybody's going to get, each program you run is going to get one node and 4 GPUs at a time. They're all, as Andreas described earlier, they're all to all connected via NVLink. So you can kind of think of them for today as just being equally far apart. If you were building a bigger program that was using many nodes, all connect, where you have NVLink within a node and then you have network across nodes, you would need to think a little bit more carefully about your communication pattern. But yeah, for today, they're equidistant. Is the tutorial being recorded? Yes. Why do compute and communication streams need to be created with different priorities in the context of Jacobi solver? I think Pouya is going to cover that after at the end of the solving session. Does nickel help with bigger systems in deciding what is close and what is not? Yes, nickel does topology discovery.
Also, let us know at some point if you guys need a hint for some of this, the to-do parts. Yeah.
You need different priorities because you need to think when is the right time to send to the neighbors that are not part of the same GPU.
I think that's a typo. It's JSC-sync-material, not materials.
Yeah. I'm sorry, that's my bad. I think I typed materials somewhere in the chat. Yeah, thank you, Arnav. How long will the access? I think that the access to the system is just for this presentation. I think the reservation will get deleted at the end of the presentation. Yeah. If you had fun, I would recommend that I mean, there's lots of good places to practice multi-GPU programming these days.
What do you think? Should we share the first hint?
Yeah, we should.
Okay.
So I'll give you guys a first hint. You have two streams if you look at the code, right? There is a push and there is a compute one. The push one is for when you are sending to your neighbors that are not on the same GPU. The compute one are for everything that is on your GPU. So the Jacobi, let's say you have 4 rows, and then the top row only needs to send to other GPU. The middle two, like, they have their neighbors, so they don't have to have any communication. That would be just compute.
I'm sorry, I was talking on mute. The question was, what do I have to change to run these labs somewhere else? The answer is, if you have Nickel working in that environment and you have CUDA working in that environment, hopefully nothing. So one of the nice things about CUDA is that it gives a virtual view, and we have these things like compute capability that let us express programs in ways that adapt to many systems and many different types of GPUs. So as long as you have a working environment, you probably just need to recompile it, and it'll run wherever you want.
Yeah, the other thing maybe is that if you look at the makefile of that particular application, you may see that there is some gen code provided to optimize for a given architecture. So in this example, we're running on the Jewels cluster, which is a bunch of A100. So depending on which environment you're running in and what kind of gen code it supports, and if it does support jitting the code to a newer generation of architecture from an older generation, and what CUDA toolkit you may have, you may need to make some changes to the makefile to be able to use the right generation code of the architecture, which is the compute and the SM number that you provide as flags to NVCC compiler, because you also have to compile the Jacobi kernel, which is the CUDA kernel code. To contrast that with the NVSHMEM side of things that we will go over, it also depends on CUDA and on the MPI bootstrap. So similar to Nickel, as long as you have CUDA and MPI available in your environments, you should mostly be able to take these code and run it there, but you may have to make some tweaks depending on the architecture and some of the MPI related dependencies, which are sometimes special in different environments.
Yeah, and if you use the really advanced stuff, there's sometimes, especially in NVSHMEM, there's some specific stuff that only works well if you have a certain kind of system. But yeah, the basics, just to run it, you should pretty much be able to run it on any system where you can get CUDA and MPI running well. And actually, you don't need MPI to run either Nickel or NVSHMEM, as we discussed earlier. It's just that these code examples use MPI. So if you didn't want to use MPI, you'd have to change the code to not use MPI anymore.
All right, in the interest of time, we're going to show you the communication pattern a little bit more in detail.
Yeah, so this is the part that you will have when you're communicating with your neighbors.
So you're basically receiving from the top, you're sending to the bottom, or you are receiving from the bottom and sending to the top. That's why you have a pair of send receive in both directions for the halo exchange. And you put those operations on your push stream, and you're doing it for the edges in the Jacobi example. And to optimize for the case where you want to fuse multiple send receives such that they can efficiently be launched on the same CUDA stream, you're using the group start and group end semantic that Pouya talked about for the overlap for the fused communication cases.
Yeah. And you can, I think there are two places we have this to do. So one is going to be on push stream, one is going to be on compute stream. There is also a question on the chat that I'm not finding the nickel com object. It's because on the top of the file you have to we have added a to-do that you have to create it.
That exercise is left for the reader. Can you explain more about the fused operations? What happens exactly between group start and group end?
Yeah, I can explain that. So imagine like in the terms of like kernel overhead, you can have we can launch 3 or 4 kernels when you have that on the stream. But when we fuse them, we would take the gap between them and run them back to back. So that one we call it a fused kernel. Oh. It's not about like having a sync when you use group start and end. It's about how the order should go on the stream.
Right, just to kind of add to what Pouya said about group start and group end, yeah, receive and send are blocking APIs. So that means your thread blocks until the API returns. If you put multiple receive and send in the same group start and group end, they essentially become non-blocking because it gives a capture view for the NCCL runtime to know that I'm expecting, an end set of operations. I'm expecting some set of operations until the last group end call happens, and so it would essentially maintain an internal work queue of those operations and dispatch them by making sure that only when the group end is called, all the operations in its internal work queue are essentially launched on the GPU.
Yeah.
Yeah, and there was a question about how the data transfers get fused. Like they go inside a super kernel, we call it, like that consists of smaller kernels that run this on the GPU.
The next question, do you know if the latencies for the sends and receives are the same? In this case, no, you don't know ahead of time what the latency of the sends and receives are going to be. But what you know is that there's going to be more coming until the end is called. Group start and group end don't carry any information about how big the transfers inside that group are going to be. So you can't make reasonable predictions about the latency. And then, of course, there's also network effects. You can't always predict the latency, even if you know the size. So no is the answer.
And just quickly on that question about the NCCL unique ID, how many NCCL unique IDs are needed? You need one NCCL unique ID. It needs to be created by one rank. So if the job is running on 4 GPUs, you can have rank 0 create the unique ID and then broadcast that to the other ranks. The reason for that is because internally in NCCL, that's going to map to a single root process being able to broadcast, communicated ID, which is some sort of a hash of IP address and port information that is used to build a bootstrap network of devices, which is for the control path communication. So whenever NCCL needs to know that how do I connect multiple queue pairs, how do I connect different endpoints, and how do I exchange, metadata and handles, which are sort of not in the critical path, it would use this bootstrap network to do that.
In order to tell, basically, the short summary is in order to tell everybody whether they're a member of the club or not, they need to have the same secret key, right? They need to be able to get, they need to have the same identifier. And so that's why it's exchanged out of band, because then everybody gets to tell the NCCL runtime, I promise I'm actually part of this group that you're creating. And then NCCL knows how to communicate.
All right. In the interest of time, should we move over to the next part of the presentation, Ben? I think.
Yeah. Sure. So next up, we're going to do the same thing with NVSHMEM. So I'm not going to go too much into the context because the code is, it's the same problem that we're solving here. So in NVSHMEM/lab4, we have Jacobi unsolved.cu. There's a few to-dos in there. You're going to need to do the communication. So where you were using NCCL send and NCCL receive before, now we're doing device initiated communication with NVSHMEM float put NBI block. So I'm going to go through this one at a time. So NVSHMEM X is it's an extension. Float is our data type. Just assume we're always using float. So this is different than in Nickel. In Nickel, you pass the type into the function. There's an enum that maps to Nickel, maps to float. We have it in NVSHMEM, we just have it in the function name. We're doing a put. NBI means non-blocking. You're going to see, I'll explain in detail how that works later. And we're doing this at the block scope, which means that within the block that calls this function, if it's sort of an all or nothing, if any thread inside a block calls a block scope function, all the threads in the block need to call a block scope function. And what you're doing there is telling the NVSHMEM runtime it is safe for you to use all the hardware resources that are assigned to this block. The API signature it takes a pointers to the source and dest, or dest and source, I should say. It takes a size, and it takes a destination PE. Next. You also are going to need to use a barrier for synchronization. So this is a host-initiated barrier. What it does is it enqueues on a CUDA stream a barrier, an NVSHMEM barrier operation that's going to launch via a kernel. So you're going to use one device NVSHMEM API and one host NVSHMEM API. For those of you who are really eager, we have a sort of bonus challenge, which is to implement a custom barrier. See if you are bored by this challenge, you can find the to-do that tells you how to do that. Next. And then finally, you're going to need to use the CUDA API, CUDA stream synchronize on the stream to pass in to make sure that the stream is finished with its work between iterations. There's a to-do for you to look at there. We'll leave this up, I think, while you're working. Okay, question from the audience. Makes sense. I think this is about the fusing, Pouya. So do you know if the latency for sends and receives are the same in this case? The answer again is no. You don't know what's going to happen ahead of time.
I think we answered that question.
We answered that.
Okay. NVSHMEM synchronization between put and wait until. Do you internally use an interrupt to wake up the receiver after putting the data and the signal? I think it's polling, right, Arnav?
Yeah, I can add some color to that. So basically what happens is when you do a put operation, it results in some sort of a store. It's a store over IP or RDMA networks, and then it's a store over NVLink if it's NVLink, and that'll land into some location in the global memory or the CUDA memory for the Pouya GPU. And what wait until will do is basically it'll keep polling on the memory location that you specify, and it will wait for that value to change from the value that the user gave it. Now, there are different semantics for how you use wait until. You can give a comparison operator which says, I want an equality check between the location I am inspecting. I want a not equal check. I want a greater than, less than. So there's flexibility around that. And then you can also use wait until with signals. So that's another aspect that I think Ben mentioned here with synchronization being a bonus question, where there are some dedicated buffers which are for signaling, which can be used for synchronizing multiple pairs of ranks. So that could mean that you have a producer send a signal and the consumer wait for that signal to arrive for unblocking the consumer for the producer's data.
And you could imagine some communication library that implements put signal instead of with a like Arnav just described with two stores and a poll. You could implement it with an active message, sort of in an interrupt-based way, but NVSHMEM doesn't do that. So you could imagine that existing.
Yeah, one example I can give is in NVSHMEM, when you do a put signal, you have a way to describe whether you want it to be a signal addition or you want it to be a signal set operation. So a set operation could translate to a store, an RDMA, right? If it's, let's say, going over an RDMA network. But in addition, will translate potentially to an RDMA atomic FAD, fetch and add. And that's basically being done to describe the semantics of, what you want to do with the signal, whether you want to accumulate at the destination the signal, or whether you just want to update the signal with some sentinel to say that it has arrived with this particular value. And in some cases, we may also implement the signal like in the put signal case that Ben talked about, where if you're going over RDMA networks, the signal could be part of your Wookiee or the payload itself. That means it's basically part of as an immediate message in RDMA, where on the receiver side you will get a completed cookie to indicate that the immediate value has arrived. So it really depends on what kind of network you're targeting and what kind of optimization makes sense for that network. And since NVSHMEM's code is sort of available for you to download and access online, you should be able to inspect the code for the different transports and see what is happening under the hood for some of the transport specific implementation.
And you can write your own transport specific implementation if you're really ambitious. Continuously polling, does that not add a big overhead?
Yeah,
so
I can color some of that. It depends on where it is polling, right? If it's polling on the GPU, then it's not really occupying your CPU resources, right? And that's what happens pretty much in all the cases, that you launch a stream that essentially has a GPU thread, which will poll on a memory location. So yes, you do burn an SM. You do burn GPU threads to do that, but that's a semantic of, what kind of operation you are doing there. There are cases where you can also not burn an SM and you can offload this to CUDA. For example, we have an operation called signal on stream and wait on stream, which essentially uses cuStream write while and wait while APIs, which are basically the CUDA stream memops APIs that allows NVSHMEM to dispatch the operation for signaling and wait to the CUDA runtime so that you don't consume a CTA or an SM for that operation. And that's something that's available in NVSHMEM 3.3.
Yeah, so that's a good point. The other thing is, if you're worried about the thread overhead, so there's a comment below that polling on the GPU is even worse. So if there's something that GPU thread could otherwise be doing, because it's all asynchronous and you're doing the wait, you can just have it be doing that work before it calls the wait. So there's not going to be a way to get around that.
And the case I mentioned where you're using it to dispatch an operation to a stream val and a wait val operation, in that case, you're not burning SMs. Those are operations that end up using a different unit inside of the GPU called the host unit, where there are semaphores that allow you to be able to synchronize on those signals and wait on those signals. So in that case, you have SMs are available to do what you want to do if you don't want to consume SMs for signaling and waiting. But remember, it comes at a cost because that latency of that operation could be higher because you have to involve synchronization between the host and the device. The point of being able to dispatch a kernel to the GPU and do signaling in that way is to minimize the latency of that signaling.
Right. So if you already have something else going on in that kernel, you can have it happen with very little latency between the kernel finishing and then the wait resolving. To get back to all the point, like NVSHMEM is here for fine-grained communication. It's when you're trying to worry about microseconds and hundreds of nanoseconds. That's when you really want to think about fusing.
And there's another question about, could we use SHMEM test to periodically check? That's not a lab that we provided. Is that a specific application that you have or an open source OpenSHMEM application? Maybe it is an open.
I think, is that just a general question? Like, I think there is there is a SHMEM test that I believe is implemented in NVSHMEM. Right?
I see. Okay. Yeah. So a test API. Okay. So a test API is another way of doing a wait until API, but I think it has a less flexibility than, let's say, a wait until API to begin with, because I think wait until allows you to give So there are ways in which you can also fuse signal and wait operations within a signal wait until API. I think the test API doesn't let you do that. I'm gonna actually hold off and not respond on that one any further because I feel I can probably do a little bit more digging on behind the scenes.
I just sent the link to the NVSHMEM test implementation.
Okay.
The documentation for the device side test.
Device test implementation. Okay.
I just sent it to the Slack.
I wasn't too sure about that if we had the equivalent test.
Yeah,
for
we
it, but I
do.
believe- Okay.
Yeah, we do.
Seems like it is. Okay. Thank you.
Yeah, I mean it uses the same signal comparison types as the weight. Yeah, so it's good to know that we have some real SHMEM experts in the audience.
Yeah, thank you for keeping me honest.
Yeah. All right. Do you guys think we should move on?
Yes.
Coming up on 10 o'clock.
Yeah. Ben, I have the next slide for you.
Okay, great. So the solution here is to use NVSHMEM float put NVI block, as we mentioned before. What we're doing here is this if statement is checking to make sure that anyone in the block with you is calling together. So this is respecting our block semantics. That's NVSHMEM specific. And then you can see that we're, I think I left in the example, the PE, the neighbor PE calculation. So that's why we have top PE is in the upward direction, bottom PE is in the downward direction. These are NVSHMEM non-blocking functions. And so in principle, even though they're sequential in the code here, they're both going to be they're going to return immediately and be executed in parallel. At least NVSHMEM runtime is allowed to do that. If you're really paying close attention today, like if you had a timer before and after those, you'd notice that that's actually not happening today. And the reason is that these are running on NVLink. And when you have NVLink system, the puts get mapped to non-blocking they get mapped to NVLink stores, which don't return until the data moves. I'm not going to go into all of the nuances about what it means to say the data moved and where it moved to, but that's just sort of a fun fact for you guys. So that's what the data movement's doing, and then NVSHMEM barrier all on stream is going to go on the compute stream. I have the dreaded several people are typing, so I probably confused more than I added. Sorry. Given NVSHMEM device-side APIs have lower latency, in what use cases would you use regular NVSHMEM APIs? That's a great question. So the way I think of it, it's sort of a crawl, walk, run, right? So let's say crawl is using MPI or MPI on the C side, on the host side to orchestrate data movement with lots of copying. Then you start walking by overlapping stuff with on-stream APIs, host side initiated, but still running on the GPU. It's going to get much, much faster. And then when you really start to squeeze out those last few microseconds, when you start to think of things like kernel launch overhead, that's when you want to start using the device APIs. So the answer is basically NVSHMEM device APIs are they require a lot more thought to use than the on-stream APIs. And that's why you would prefer on-stream, because they're still really fast and they don't require nearly as much thought. Arnav, can I answer one more?
Go ahead.
Couple more. Okay, so the scaling limitations one I'm going to come back to because it requires a more complicated answer. So in which case would it actually be non-blocking? Don't NVIDIA GPUs most always use NVLink? Great question. No. So when you're using one node, you often will end up using NVLink. When you're using a multi-node system, you're going to have a mix of NVLink and network. So when we say network, I mean like RDMA, Rocky or InfiniBand. In those cases, Yeah. Okay. Documentation link.
In the
Yes.
interest of time, should we just hold on to some of the questions and get back to them
Yes.
later?
Yes.
Okay.
Yes.
All right. Great. All right. Thank you so much, Ben and Pouya, for giving us an introduction to Nickel and NVSHMEM and helping us understand how to write applications, both Hello World as well as as well as a real life workload like Jacobi Solver. I'll be now covering some of the new and upcoming features in Nickel and NVSHMEM, focusing on two labs on some of the newer features that were released in Nickel 2.27 and NVSHMEM 3.3. So symmetric memory, this is one of the newer features in Nickel 2.27. It was released as part of our May release. It's a foundation capability in Nickel that allows you to do high performance, low latency collective operations. The way this works is that when you have memory buffers that are allocated in an identical virtual address space across ranks, Nickel can optimize the collective communication by eliminating or reducing synchronization overheads and improving bandwidth efficiency. So the way to think about this is that if you have an application that allocates its own user buffers that may or may not use CUDA APIs, or they may use a Nickel memalloc, which is a convenience functions around some of the CUDA VMM APIs, then you can register this buffer with Nickel to create a symmetric abstraction, which is the same identical virtual address space across all ranks, either lingering at the same offset or not, to provide what's called a symmetric window. And Nickel provides for this a new API called Nickel Com Window Register. This is a collective API, which means all the ranks in your communicator need to invoke this API with the location of the buffer and the size, and it would return a window object that essentially manages the symmetric virtual address space abstracted behind the communicator. You can provide flags to this to indicate whether you want the window to be default or symmetric. Once you've done this operation, and Nickel is hinted that it needs to be able to manage this buffer using symmetric windows. When Nickel sees an operation like an all reduce, an all gather, or a reduce scatter, any collective operation with that buffer, it would internally know that it needs to be able to use the corresponding window, which is the identical virtual address space across ranks, along with the concepts of the symmetric memory to be able to optimize communication. But what I mean by optimizing communication is that Nickel has a broad variety of kernels that it builds for. It builds for kernels that can stage communication using intermediate buffers because some of the systems may not support direct communication from the GPU buffers. It can do user buffer-based communication, in which case you directly read and write to the buffer that the user provides. Or in this example, it can use a symmetric window, which is an identical virtual address space across ranks, and optimize communication using some of the protocols or some of the features in the hardware like NVLink Sharp. And by doing so, some of the operations like an all reduce, which are accelerated in the switch, it can take advantage of those features without performing any synchronization overheads, which would, in traditional kernels, verify if your addresses and size are symmetric across ranks before using them. Whereas in the newer kernels, you're eliminating those overheads, and you would be able to dispatch the operation in a very similar way that NVSHMEM all reduce would also work. Once this operation is completed and you're done with using that window, you would call a Nickel Com window deregister operation to release access to that particular window object. Here I have some plots that were recently collected on a GP200 based NVL72 system for a workload size of about 32 ranks in a communicator. It contrasts the performance of Nickel 226 and Nickel 227 release between the small to medium and medium to large message size. As you can see that depending on what message size you're operating on, your performance improvement could be drastically higher or in the middle range. So you have about 7 to 5x improvement in small to medium message sizes, and in the large message size, you have about 3x improvement. I've also attached a link to the blog post with symmetric memory. It was published also pretty recently in, I think, the last few months or so. So the link of the blog is also here for your reference. You can look at that offline, and if you have any questions, please feel to shoot us those questions on Slack as well. The lab that we have for today on symmetric kernels will allow you to get familiarized with these window registration and deregistration API. So if you now look inside the lab 5 folder in Nickel, you will see an application called Nickel Symmetric, and you should just build that application and run the application. The instruction to build it would just be make, and then to run it would just be make run. What the application is doing is that this application would have a communicator that's initialized. and you would have to perform an all gather operation between the ranks, and it would use the symmetric window register and deregister to accelerate the communication. There are to-dos in this exercise, which means you need to go look at those to-dos and fill and apply based on the registration APIs and the collective APIs that I have flashed on the screen here. So I'll give people a few minutes so that they can inspect what's happening inside of the code and look at the to-dos and then decide how to apply these APIs to them. So it seems like there is a question about nickel and NVSHMEM being combined in the future. I'll get to that towards the end of the presentation. It's a pretty heavyweight question. We have some slides that also talk about the roadmap for the two libraries and what's coming. So I request you to hold on to that particular question. I will address it towards the end of the presentation.
There's a question about, can we give a quick start guide? Yes, I think at the end of the presentation, there's a list of things you can go look at to get started. I can also just send you those quick start links in that thread that you started on Slack. I'll do that now.
Yeah, another good one to share, Ben, is the CUDA C++ programming guide. It has a good introduction to threads, blocks, and warps as well.
Yeah. Also Jeff's GPU mode presentation that was linked earlier in the chat.
A key thing to remember, if you don't make any changes to the to-do and you try to run them as is, the example should not run for you. So please give it a try. If you have any questions that you are running into, if you have any problems that you run into in terms of executing the example, please feel free to reach out. There is an option in the command line. There's a command line interface in the example that allows you to tune it for different message sizes. By default, I believe it's about a kilobyte of message size, but you can tune that to a larger size. Just look at the code at the parse usage function or so, and you should have a -b parameter that allows you to be able to use a larger message size buffer. And the example should do data verification checks at the end as well for you. Okay, in the interest of time, I am going to move over to the next topic for the comms library. If you have some issues with the symmetric memory exercise, please do mention to us. I just want to make sure that you guys have been able to run this. Okay, I see there's a question before I move on. Are the window APIs async? No, they're not asynchronous. They are collective, meaning that all participants need to invoke that API. So we don't support today a mechanism to make to issue these operations asynchronously. However, I will take that feedback and check back with the team if there are plans to do that later. All right, I'm going to introduce the next new feature in NVSHMEM and explain that. I believe I can come back to the nickel symmetric memory in case folks need some more time to look at that example and have some more questions. But I just want to give people a chance, those who have been able to complete the exercise, to look at the new feature in NVSHMEM and try that exercise as well. So the next feature that we have is the feature that we released in NVSHMEM 3.3. It's called NVSHMEM for Pi. It's a Python library, which is an official language binding for NVSHMEM. It provides a Pythonic interface to NVSHMEM library. The purpose of this project, or the purpose of this particular library, was to enable Python applications, specifically AI and HPC applications, to leverage high performance PGAS abstractions and programming models for GPU-centric communications as directly in Python. So we realized that oftentimes people were trying to write their own custom binding solutions, or we realized that there are cases where people are still using abstractions of like MPI for pi and SHMEM for pi, and trying to copy the data between GPU and CPU while trying to use it in a Python application, which can hurt performance. So to address that particular need, and we decided to provide a first-class native Python APIs for NVSHMEM. We have attached a link to the documentation as well for this. The way you want to think about this API and how to use them is very similar to the C APIs, but with for Python users. So for example, in a C API, you would initialize the NVSHMEM runtime through the help of the MPI bootstrap. Very similar to this, in the Python APIs, you would initialize NVSHMEM using a CUDA device and the MPI communicator. This allows you the flexibility that, if you have MPI for Python applications already and you have a communicator that's created, you can just pass that as is, and NVSHMEM runtime would be able to understand and interpret that and use that, lower that down to an MPI COM object that can allow the NVSHMEM C library to bootstrap with the MPI communicator. We also support different methods for initialization. MPI is one of them. The UID bootstrap, similar to the Nichols, the UID bootstrap is also supported, in which case if for application users who don't have a dependency on MPI and they would want to be able to use any launcher and just have an out-of-band mechanism for communicating metadata, they can also take advantage of that in Python. So the difference there would be is that you provide a rank and a size, and you would say through a hint that I'm using the UID method to initialize. Now, once the NVSHMEM runtime is initialized, you're now allowed to be able to allocate tensors from symmetric memory. So Ben talked about NVSHMEM malloc being the API that allows you to give a symmetric abstraction or a symmetric tensor, which is backed by memory on all the GPUs, and you have a virtual memory address that you can use in an application. So we wrap that up inside a torch tensor or a CuPy array. We realized that a lot of HPC and AI users of Python like to use their own array libraries, and so we respected that, and to allow for interoperability, we wrap the symmetric memory abstractions through the tensor and the array APIs, and we return that as an object for the user to go play with. So that these are convenience APIs for us to use the torch tensor. They take in a tuple of elements and a shape and a stride, and they also take in a data type, which is a torch data type, or it could be the CuPy data type, or it could be the NumPy data type. And then once these tensors are allocated, now you may want to run a collective or a point-to-point operation. A collective operation could be you're doing an alt reduce. That alt reduce takes in the team, which is a group of P's you're operating on. This is different from Nichols communicator, but similar in certain ways too. It takes in a tensor argument, which is the tensor symmetric tensor that you have created in the previous step. It takes in the reduce operand, which is the sum in this example. So in this example, what we're doing is we're doing an all reduce operation where we are accumulating the results from all the ranks and we're distributing that results to all the ranks. And so the accumulation operation is the sum operation that we have here. We support other reduction operations just like OpenSHMEM does, which could be min, max, product, max, log, etc. And additionally, because we're NVSHMEM, we are an implementation of OpenSHMEM on NVIDIA GPUs. We also support stream-aware API. So we take in a stream argument. Now, one thing that you don't see in this example in front of you is how is the CUDA device managed? How is the CUDA stream managed? Well, CUDA has been working on providing Pythonic abstractions for the past few years, and one of the libraries that they provide for this is CUDA Core. So we build on top of the abstractions that CUDA Core provides in Python for device and for stream and for events, and we just use those abstractions so that application users who are already using CUDA Core abstractions, it could be a cuQuantum user, it could be a CuPy numeric user, you could be a Rapids user who's using some sort of a Spark library, or you could be a Rapids memory manager user, and etc., what have you. Pick your favorite Python project that uses GPU today and that uses CUDA Core. And we can work with that project because those device abstractions can then be passed inside these APIs. And now once the all reduce operation is dispatched to the stream, you obviously need to synchronize with the stream. So that would be an explicit step to synchronize with the stream, but that's again a CUDA Code or a CUDA Python API. Once that operation is done, you would finalize the NVSHMEM runtime to indicate that I want to tear down the runtime and I'm done with NVSHMEM in this particular example. So this is a walkthrough of how the different steps are involved in being able to use a Pythonic APIs. The lab that we have for this is the lab 6, which should be in the NVSHMEM lab 6 folder. You should see there exists two files, the put.py and the putsignal.py. The put.py is an implementation of a one-sided put operation that's moving data from rank 0 to rank 1. And it's using Barrier to synchronize this operation. Now, as Ben mentioned about this earlier, Barrier is a collective operation, which is a heavyweight synchronization operation. You can optimize that by implementing a put signal based or a signal weight based signaling and synchronization mechanism. So I have examples of the definitions of the put signal and the signal weight API on the screen here. So the exercise that you have is to run the put signal example and optimize the communication to not use the barrier, but to use the put signal and the signal weight API. Let us know at any point if it's not clear what you need to do. The to-do should be there on the screen. They've also attached hyperlinks, and Ben has written a really good README that talks about how to set up your Python virtual environment, being able to install the enrichment for Py dependencies, and then being able to execute the example. And you would need to fill in the to-do parts for the example to run successfully.
Yeah, so the make file for this one, I think only does make run. So you'll have to build the environment manually. There's description in the README for how to do that. Let us know if you have problems. Thank you for pointing out the typo in the README. Yeah, there shouldn't be parentheses. There should be curly brackets around PWD. That's true.
Thank you. Thank you so much for pointing it out. I think when I was running the example myself, I may have not used the PWD and run into this, but thank you for pointing it out.
As you guys probably can guess, being busy comms library developers, we pulled together a lot of this recently, especially the READMEs, right? The documentation always comes last. Arnav, Pouya, do you know if these the code samples are going to be distributed or just the slides?
I do not have that information actually.
Okay.
We can check with the Hot Eye team offline.
Yeah. Well, if the code samples are going to be distributed, we will make sure to clean up these little typos and stuff before we do that. Okay, you could not find a version for lib NVIDIA NVSHMEM Q12.
Actually, you may not
I
even.
think you don't want lib. I think you just want NVIDIA NVSHMEM Q12. Let me test that on my side real quick.
And I think if you just do pip install
NVSHMEM for Pi.
yeah, NVSHMEM for Pi dash Q12, that should install the NVSHMEM and their associated dependencies. And
Yeah.
just for today, we've also added a requirements.txt, so you can just do pip install dash r requirements.txt. So anything that's missed would be picked as part of that too. But it should be as simple as pip installing NVSHMEM for Pi dash Q12.
Yeah. So yeah, that was the issue, by the way. It's that there's no lib on. So the wheel gets named lib NVIDIA NVSHMEM, but the package, the PyPI package is called NVIDIA NVSHMEM. But yeah, like Arnav was saying, the pip dependency resolver should take care of this for you. So if you just do pip install NVSHMEM for Pi dash Q12, it will pull in NVIDIA NVSHMEM as well. And make sure you install the requirements.txt because I think the example uses CuPy. And so the requirements text will pull in CuPy, which is not a hard dependency of NVSHMEM for Pi.
And just to clarify on why the packages are named the way they are, so NVSHMEM for Pi can support multiple CUDA versions. So, the CUDA suffix is basically something that's added to indicate whether this is NVSHMEM for CUDA 11, CUDA 12, or CUDA 13, and for other CUDA versions. So we support for CUDA 12, so which is why the Q12 suffix is at the very end. This is similar to some of the other CUDA Python packages that are out there today.
Yep.
All right, seems like people are still installing the NVSHMEM dependencies. They haven't gotten around to running the example yet.
Take your time.
Okay, yeah. So if you're seeing an NVSHMEM error found unfreed memory object, that is actually good. So this is NVSHMEM for Pi. There's a description of this in the NVSHMEM for Pi docs that I posted. NVSHMEM for Pi, similar to SHMEM for Pi and MPI for Pi, requires that the user calls NVSHMEM free. Basically, you have to explicitly tell NVSHMEM, I'm done using this tensor. So if you're getting to that point, what's happening is the NVSHMEM for Pi is calling finalize. It's checking to make sure you followed the rules, and it's finding that you didn't follow the rules because our example doesn't without some modification. And it's warning you that next time you run the program, please follow the rules. So you can resolve that by adding nvshmem.core.free tensor, or I think just nvshmem.free tensor, because we imported nvshmem.core as nvshmem.
And it's also a good thing. That means you're running the put signal example, which should not work unless you fill the to-dos,
Yeah.
which include things like Ben said, the free tensor API as well. I didn't mention the free tensor API in the example before. That thank you for pointing it out, Ben. But yes, he's correct that once you're done with your usage of the tensor, you need to call an nvshmem.tensor free tensor to essentially release the tensor back to the nvshmem runtime. And the reason for that is also because allocation and freeing operations in NVSHMEM are collective operations because we need the tensors to be symmetric across all ranks. Symmetricity is important for being able to take advantage of the one-sided nature of these communication operation. Without that, we would not be able to essentially know the address of the peer while being on one of the ranks. We would have to do that exchange every time we invoke the API, which would hurt performance and not make it one-sided protocol, basically. So this is something that we do realize that the Python community is not very well accustomed to, because they are used to the garbage collector essentially releasing the resources for them whenever the operation is done. But we have taken care by making sure that these operations don't interfere with the garbage collector, because we internally track references to these objects to make sure the garbage collector never frees them whenever they go out of scope, or if the objects were intentionally deleted by the user for whatever reason. And we give them enough exceptions, warnings, and logs to indicate that they need to clean up after themselves and their code for these objects. But they're free to use this tensor like any way they please in a torch operation or a CuPy operation. It doesn't behave any different other than the fact that you need to explicitly free this object.
Yeah, one of the principles of NVSHMEM for Pi is basically make it as easy to use correctly as possible and make it as hard to use wrong as possible. So if you ever encounter a situation where the tensor goes out of scope, you will get an exception raised. And you will be able to, you'll be told, like, don't do that, you leaked memory. But we do protect you, like Arnav was describing. We by not calling free in a non-deterministic order, we protect you from deadlocks. So if we just unconditionally called free every time the tensor went out of scope, you'd be exposed to deadlocks. Yeah, the difference between free array and free tensor is that array is for CuPy arrays and tensor is for torch tensors. So I actually don't remember if this example is using torch tensors or CuPy arrays. Probably CuPy arrays, since array worked for you. But they're similar, basically.
Yeah, I think on the top of my head, it's a CuPy array. You're right. Yeah.
Yeah, basically CuPy arrays and torch tensors are both wrappers for n-dimensional arrays with different limitations and benefits. And obviously torch tensors plug into torch functions, CuPy arrays plug into CuPy functions. Internally, yeah, go ahead.
One thing to point out, though, is that both of them support what's called DLPAC protocol, which is a zero-copy data interchange protocol that allows you to go from torch tensors to CuPy arrays without copying the data. And this is sort of important because, the point of using these array abstractions is that you can allocate buffer in GPU memory, but then you can pass it as a container through a tensor or an array object for the applications to use them. And then they can move they can essentially interchange this from an array to a torch format or from a torch to another format as long as they support DLPAC protocol. And we intend to be DLPAC compliant for these memory management APIs.
Yeah, and what you end up getting is a view. So you end up getting a torch tensor compatible view into NVSHMEM symmetric memory. The important part about it being a view is that NVSHMEM is your allocator. Like NVSHMEM is the source of truth that's giving you the memory, because it comes from the symmetric heap, and NVSHMEM is in charge of the symmetric heap. So when you like, it's not like Torch is going to call CUDA malloc and build tensors from torch memory. We have to build the torch tensors from NVSHMEM symmetric memory and then give it to you. It seems like at least some people have been able to run this. Has any, I guess, can you comment in the chat if you've been able to optimize away the barrier?
If you run the put example that should have the barrier, you need to run the put signal and improve that using put signal and signal weight APIs, just to recap.
Yeah.
Okay, there's a question about is pip install NVSHMEM for Pi Q12 instead of NVIDIA NVSHMEM Q12. Ben, do you want to take that question?
Yeah, so yes, those packages both exist. NVIDIA NVSHMEM Q12 is the package that just contains all of the underlying NVSHMEM libraries, like the .so files and .a files that are part of NVSHMEM. NVSHMEM for Pi contains all the Python and C files that wrap around those and then expose it into Python. So you're going to need both. But if you install NVSHMEM for Pi Q12, it will automatically pull in NVIDIA NVSHMEM Q12 as well because it's a dependency.
One thing to point out is that NVSHMEM for Pi, when it's distributed, there are only dependencies which are hard dependencies are CUDA core, as well as the lib NVIDIA NVSHMEM 12, a Q12, or the CUDA specific dependent, the QX suffix. As you know, obviously the CUDA code, because we use those abstractions, and NVIDIA and the NVSHMEM C library because you need those libraries in order to use NVSHMEM for Pi interface. But we don't have a hard dependency on MPI for Pi, Torch, or CuPi. And the reason for doing that is because we do realize that there are users who may have their own array libraries or may have their own bootstrap interfaces. And so we don't necessarily enforce users to bring in those dependencies in order to use NVSHMEM. They can bring in their own array interface as long as it supports DLPAC protocol. We can build APIs to support that in the future for them. But for now, we decided to operate with Torch and CuPi because they are widely adopted and used across the board for a lot of Python applications. MPI for Pi, like I said, is not a hard dependency because we also allow a UID bootstrap specific initialization method that doesn't take in MPI object, and you can just provide the rank, the size, similar to Nickel, and the UID. And it would initialize the NVSHMEM runtime internally. So that gives you the launcher agnostic capabilities where you're not necessarily tied to using MPI run to launch your application. You can have your own custom launcher that has its own out-of-band mechanism to distribute UIDs, and you can use that with NVSHMEM as well.
Yeah, we also depend on a few silly things like Cython and NumPy and things that everybody has installed everywhere already. But the dependencies are pretty minimal. Like, you pull in order tens of megabytes of stuff, I think, if you install cold. Would you explain what signal op is used for? Yeah. So the signal op is the operation you want the signal to perform. So the way a put signal works, you can think about it as doing two things. First, it does a put, it moves the data for you. And then when it's done moving the data, it does a signal operation. And the signal operation is going to copy or set or do something. I'll get to that in a moment. Some extra data, and that data it's guaranteed that the signal operation happens after the put is complete, and the signal op tells the signal what to do. So the signal op takes an enum that tells it to do something like signal add or signal set. So you can say, for example, do a put signal, and what that does is with a signal set, and what that does is first it copies the data for you, and then when it's done, it sets the signal flag to that thing that you passed in, the signal val. And then the receiving side can call wait, and then it can use the wait to test. I think Pouya is also answering that. Yeah, he sent the link to the signal op flag.
So yeah, as Ben was describing, and to add to what I had said earlier about signal, like you can do additions, you can do set operations, and that's similar to the NVSHMEM, to the OpenSHMEM set, and add semantics for signals as well.
Right, and the key part of this exercise is basically like, because the signal and the wait happen separately, you can optimize away the barrier, and it's still safe to run the program. You'll get the correct output without a barrier. So this is an example. Basically, this is an example of a fine-grained synchronization where you're not using as heavyweight a barrier. You could imagine a much more complicated program where you're using many of these signals all at once instead of using one global barrier, and you can make some serious performance impact.
Yeah, so just to, again, I'm kind of giving a little bit nuggets as Ben is thinking about things, and I'm realizing that those things are interesting. Mixture of expert models and AI workloads do this custom all-to-all communication pattern like dispatch and combine that probably DeepSeek and Perplexity also did. And so those implementations on the device side do use put signal and signal and wait. And the reason they do that is because put allows them to move data. Put signal allows them to move data and the signal in a given order. Wait allows them to wait on that signal. And the reason they need those specific operations is because when you're doing the dispatch or combine operation for at least the DeepSeek's implementation of that custom kernel, then the signal is used to distribute how many tokens should the receiver rank expect, which is essentially the number of those tokens are essentially messages that you exchange between experts in a mixture of experts model. So it would wait for a count for n number of tokens to expect. And so the way you can think about signal and wait is that signal would essentially send you in with, if it's a signal add, then it would accumulate that count at the destination for you. Versus if it is a signal set, then it would just signal to the receiver that I'm done with the data transfer, right? So if I want to send in a count of tokens to be accumulated at the destination, I would use a signal add. Whereas if I want to do just indicate that once I'm finishing transferring all of my tokens to a given expert, then I'm done transferring that particular message, I would just use a signal set. So that's a good way to kind of think about, how to use signal add versus signal set in a real life workload like, an all-to-all.
Are there benefits / optimizations within NVSHMEM to use put signal over put fence atomic set? One silly one I can think of right away is you don't have to think about the fence, which is a really big programmer-centric optimization, in my opinion. We take care of that for you. Arnav, are there perf optimizations as well?
Yeah, so I can add some color to that. So imagine if you were doing a put with a fence followed by a signal. Now, depending on what kind of network you're going on, that fence can be expensive. So for example, if you're going over NVLink, a put and a fence, put would just be a store over NVLink. A fence may be as expensive as a thread fence system operation because you just want to make sure that your stores that you submitted previously have reached a particular point of consistency so that when the set, or when the signal is sent subsequently, it doesn't get reordered before the puts, right? So you would issue the fence operation to order the put and the signal, but it's an expensive operation that happens right now. If you were to now do this operation over the network, then maybe doing a put followed by a signal, put and a fence and a signal would result in basically having your puts and your signals being two different messages to your destination over that queue pair, meaning they could be two different RDMA commands like writes or writes and atomics. And if you recall early in the presentation, I did talk about one particular optimization that's interesting, which you could do is something like an RDMA write with immediate, where the signal could be the payload in the Wookiee, which is the immediate data that the receiver could receive as soon as the data is received. So it doesn't necessarily need to be two discrete messages, which is an RDMA write and an RDMA atomic. It could just be an RDMA write with immediate, which contains the signal value that you want. And then that could be essentially returned to you on the destination through a receiver completion queue entry. It doesn't let you do the atomic characteristics if you want to do that, but it at least allows you to optimize puts and signals in a single message if that's possible. So that's a performance optimization, and why you may want to do them in one versus another. But I have seen often in practice that put signal is often used when you want to synchronize at the very last message of sending. So in the case of the all-to-all for mixture of experts, that was the common use case where you would do a lot of puts followed by a put signal that essentially synchronizes to make sure that all those puts that came prior have been written before the signal is observed at the destination. But it does come at the cost that you have to send the signal and the data in the same single message. So depending on what network you're using, you may or may not want to optimize it. We have observed that there are some users who don't want to use fence and quiet operations, which are again synchronization operations, because they are expensive, because they either incur, like I said, on the NVLink, a threat fence system, or the equivalent on the IP side. But it's really a programmer's choice of how they want to construct those kernels, because they may have networks where these signals and their puts get reordered even if you submit them in a specific order from the point of the origin, right? So imagine if you're doing something like a network which has multipathing, where depending on, and you end up using multiple paths by dispatching put and signal to two different paths, like two different queue pairs for in RDMA, then they would definitely get reordered. Then you can't depend on the order of the signal to arrive before the data, unless you have some other mechanism on the receiver side to reorder them in software, or maybe in your custom transport if you're using your own transport. So it really depends on what kind of a network you're operating on and how you want to write these custom kernels for those operations in the case of device APIs, or in the case of host APIs, what kind of operation you want to use with on-stream interfaces.
Yeah, and there are networks, I'm not going to name them, but there are networks which, if you put things in the same, queue pair, even if they're on the same queue pair, you might have out of order things happen. If things are getting sprayed out multipath and then collapsed somewhere else, or things like that can happen, and sometimes you need to prepare for that depending on your networking hardware.
Okay, it seems like we spent quite a lot of time on this particular lab. I know we had a lot of dependencies to install and get accustomed to it. But there are some, but I think we want to move on. I do see a question though. It says that, but I'm seeing an error if I do signal wait with an unexpected operand, which is remote PE.
I need to check. I'll reach out to you on Slack.
Okay. Thanks, Ben. Thank you for following up on that question. So as some of you may have been able to run this example or may not, I will have some time. It seems like we will have some time towards the end of the presentation to go back to some of the labs in case something was missed. And we can cover that towards the end as well, and answer some of your questions there too. But I will move on in order to complete the rest of the talk. So all right, so now here are some takeaways from some of the exercises that we did today, and also the material that Ben and Pouya covered about the capabilities of Nickel and NVSHMEM. So both libraries enable GPU-centric communication. That's a key thing we want to highlight to people. GPU-centric means they allow you to be able to move data from either host-initiated operations or device-initiated operations, or both, right? And they necessarily may or may not have methods to be able to copy data back between the host to device, which can become a point of synchronization or overheads, and can hurt performance. So they are essentially geared for GPU-centric communication. Some key differences to think about the two libraries today, right? So Nickel has been operating on a two-sided semantic, which is one side calls send, the other side calls receive, or in case of collective, you need all participants to participate in the operation. NVSHMEM, on the other hand, provides a more one-sided programming model, which is, as Ben mentioned, one side is involved either putting the data or getting the data, or in the case of signaling, one side would do a signal and the other side would do a wait, but that again is by nature two-sided, being implemented using one-sided APIs. One other big difference between the programming model is that Nickel operates on the concept of communicators, which are created using a set of ranks that the user determines. So it's not a communicator on the entire world. It could also be that you want to make a communicator on a subset of ranks, and you're free to choose how you want to construct that communicator. You're not necessarily locked in to using a COM world only model or a COM node only model. You can decide what you want to do with the way you decide how to create your communicator. Whereas NVSHMEM operates on a global runtime. Now, this is the design paradigm that NVSHMEM inherits from OpenSHMEM, right? This is a unified global runtime, which has a theme-based abstraction that allows you to make a group of PEs, but they're all belonging to that global runtime. Also, NVSHMEM has a symmetric memory management model, which allows you to allocate and register symmetric memory, but it operates on a global runtime, which is the list of all processes in your world. Essentially, you will be able to have a view of that single symmetric heap that NVSHMEM provides. Nickel provides on-stream collective APIs, which are basically, it provides on-stream collective APIs, which are stream-aware, meaning they are CUDA. You can dispatch these operations on a CUDA stream. It also provides point-to-point APIs for communication using send-receive, whereas NVSHMEM provides the on-stream and the device-initiated collectives, and the point-to-point, on-stream, and device-initiated put and get APIs. So, these are the differences between the programming models and their usages today. There's also a lot of similarity between these two libraries. Now, we covered how you can do low latency symmetric kernels with Nickel in Lab 5, right? And those are also capability that you have in NVSHMEM. So that's a common capability that exists in both libraries. Both libraries allow you to be able to interoperate with MPI and also other well-supported communication libraries out there. So if you have another communication library that is doing either out-of-band or data path communication, and you want to use that to bootstrap Nickel or NVSHMEM, you can do that using the UID bootstrap for both of them. So it interoperates well with that. It also makes use of high-performance communication technologies like GPU Direct RDMA. So we didn't go into the details of GPU Direct RDMA in today's presentation, but the short version of that is you have data in GPU memory that you want to move from one GPU to another, and you have a NIC that's connected to that GPU, either in the same PCI switch or somehow connected using a proprietary chip-to-chip interconnect, like there is one on Grace Blackwell. And you want to be able to move data from the GPU on the one side to the GPU on the other side using the NIC. And you don't want to copy that data to CPU memory. That technology is called GPU Direct RDMA, and both Nickel and NVSHMEM make use of that in their transports, their RDMA transports. They also provide communication over NVLink. I think Ben covered that during the NVSHMEM part of the presentation, and also the labs that you ran today were running on a set of A100 nodes, which were connected using NVLink 3. That is something that was already covered. That is something that you already got to experience with while you were running your workloads. Both Nickel and NVSHMEM support NVLink Sharp, which is an acceleration protocol inside the switch that allows you to do, switch-based reduction operations as well as multicast or broadcast operations, which are primarily used for accelerating the latency and bandwidth for collectives like all reduce, scatter, all gather. And both of them provide CUDA-aware, CUDA stream-aware, asynchronous GPU to GPU bulk and fine-grained communication APIs. So these are some of the takeaways that we hope that you would have from today's talk and today's presentation. Before we go, we do want to talk a lot about our roadmap and what's coming. We want to give you a little bit preview into what to expect from both libraries, because there are similarities and there are some differences as well. So Nickel, the last release was 227. It was in May. 2025. The two key features that were as part of that release was symmetric memory and communicator shrink. Symmetric memory is a feature that we went over in Lab 5. Communicator shrink is a fault tolerance feature that Nickel allows that in the scenario that you may have a workload where some of the rank die because either there is a fault or there is some sort of an operation that's fatal, you want to be able to shrink your communicator to operate on the subset of ranks. You can do that using the Nickel Com Shrink API. It's available already in 227. Coming in 228, which is going to be a release in September, we will add collectives that can take advantage of the copy engine. Copy engine, for those of you who don't know, is the hardware unit that's exposed through CUDA memcopy async APIs. So what we are doing with this particular feature is that we have seen users who want to be able to mix Nickel collectives or comms collective operations with their own operations. Either they are collective or point-to-point, or there are other compute operations which are being launched also on the same CUDA stream, or maybe on a different CUDA stream for the case that Pouya talked about, where you are overlapping operations. And so we realized that oftentimes you want to be able to move data, but you don't want to spare threads on the GPU for the data movement. And so to alleviate some of that, we provided this capability where you can have a 0SM based data movement protocol, which is the copy engine based collectives. Some of the collectives like all gather, all to all, broadcast, these will be supported using the copy engine. And we have an early preview of our release already live on GitHub. So if you go to the Nickel GitHub, you should see the early preview for 228 out there. We're also going to be adding device APIs. So, the developers of Nickel or the community of Nickel has requested heavily for being able to write, custom collectives, even with using the Nickel programming model. And so we are going to be supporting device APIs in Nickel so that users can have the right toolbox to be able to use and develop, collective and being able to write custom communication kernel or fused kernels. I'll talk a little bit about the differences between NVSHMEM and Nickel in the context of device APIs towards the end. So if you have any question around that, please hold on to that. Nickel in the subsequent releases would also provide APIs for additional fault tolerance features like communicator grow. So we have also users who are of AI and HPC workloads who are saying that we want to be able to have hot spares that we can use to once a particular rank dies or a node dies or certain participants in my communicator they fault. We want to be able to now make a new communicator, which can essentially grow from an existing communicator to include these sort of new ranks to sort of back up the existing ranks that have failed. And to do that, we're providing an abstraction called communicator grow. And we'll also be providing some more latency optimizations in that release to address some of the latency concerns of the existing collective and point-to-point APIs. Lastly, on the NVSHMEM side of the roadmap, so we had our 3.3 release, which was the NVSHMEM release that provided the NVSHMEM for Pi product that you actually operated with. So that's the Lab 6 that you worked on. We had the NVSHMEM for Pi's first release as part of 3.3. Since then till now, we have been making a lot of open source contributions. As you know, NVSHMEM has been adopted a lot by some of the existing MOE kernel libraries like DeepEP from DeepSeek. There's also Perplexity's kernels, which uses NVSHMEM. They have their own custom collectives for it. There's FlashInfer, who is trying to use NVSHMEM for its communication, for its kernel authoring. And so we have been working actively with the open source community to help collaborate on improving the deployment of NVSHMEM or porting some of their custom bindings to use the NVSHMEM Python interface and the links to the PRs have been attached here. In our release in September, we'll be adding support for new platforms such as the GB200 and the GB300 based platforms, which use direct NIC capabilities. We'll also be adding some improvements for expert parallelism support that some of the open source community have requested for. And then subsequently in our NVSHMEM 3.5 release, we will be covering both features in our C library and in our Python library. So on the C side, we would be adding improvements to IBGDA. Now, we didn't cover IBGDA in today's presentation, but a way to think about IBGDA is that IBGDA stands for InfiniBand GPU Direct Async Transport. It's basically a new kind of transport which doesn't involve the CPU in the control path. What I mean by that is today, when you have to move data from GPU to GPU, and you use GPU Direct RDMA to do that over the network, you have to offload these operations to a proxy thread on the CPU, so that you launch a kernel, it would dispatch operations to a proxy thread on the CPU, which would interface with the NIC to be able to do operations like IB verbs post send or IBV poll CQ, which are verbs commands to be able to do RDMA read write operations. Now with IBGDA, what happens is those operations can be directly programmed by the GPU thread. So you have kernels which are preparing the data and doing the compute operations on those data, and now they need to dispatch the communication operation in a more fine-grained way. And so we have IBGDA transport that allows us to do this. And we've used this transport for a few years now, and a lot of the mixture of expert all to all use cases of fine-grained communication, we do see a lot of benefits with using IBGDA transport. And so to add to that, we're providing some additional features to improve its API surface. So for example, users have requested that they want to be able to select which queue pair they use to do data movement operations. So in the scenario when there are multiple queue pairs, which means that it could be multiple paths in your networks, user can decide how the data goes in which path, right? It gives more flexibility, more control of the users to do multi-pathing. And also we'll be adding copy engine based collectives because again, users of NVSHMEM need to also do overlapping of computer and communication operations. And so they've requested for similar capabilities. So we would be adding that. And on the NVSHMEM for Pi side, one of the key things that we will be providing in our October release is first class citizen APIs in number CUDA DSL, which is a dialect that allows you to write kernels in Python directly. So we will be exposing our device APIs directly in Python. So that means the example that you saw when you were writing the put and the put barrier or the put signal and the signal wait, which were host initiated APIs. Now those same set of APIs will be exposed in the device, which means you can write a number CUDA kernel that essentially does an NVSHMEM put or an NVSHMEM get or an NVSHMEM barrier. And there are some more improvements that we're adding towards, team management so that users can create more teams in a more arbitrary way. And some of the array APIs that we have, we're also going to be exposing convenience methods to be able to access, the multicast memory that is often used for NVLink shard protocol, and more features like that. So that's kind of a preview into what's coming next. Lastly, I do want to point out that we have a lot of resources on both libraries that are available. The API documentation, the quick start resource, they are all the hyperlinked up here. We've also attached a link to a few blogs that have been published in the past few years, which we found a lot of the users of NVSHMEM and Nickel we found that users found this. We observed that a lot of users requested for more details about how IBGDA works, how application portability works in NVSHMEM. How do you tune Nickel to get the most performance out of it, or how do you make Nickel more resilient? Or how do you improve the low latency or the collective operations, the latency of collective operations or the bandwidth efficiency of collective operations? So to address all of these different areas that are often a key pain point for developers of Nickel or NVSHMEM or for developers of any GPU-centric communication, we added blogs to help the community onboard to the libraries, use the new features that we have, give us feedback. I've also attached a link to a talk, which is by a talk that was, as I mentioned earlier, from Jeff Hammond, another principal contributor in our group. He talks a lot about the history and evolution of MPI, OpenSHMEM, and towards contrasting that to Nickel and NVSHMEM. So if you get a chance, please do look at that talk. I really highly encourage you. It's a really interesting talk that he gave. We've also provided links to the Nickel and the NVSHMEM developer forums and GitHubs. So the QR codes are up there. You can check them out. One thing if I didn't mention, I should mention, NVSHMEM is coming to GitHub soon. That's been a really important area that a community has requested for. We have not been on GitHub for quite some time, and we are now trying to bridge that gap for the community so that you should be able to git clone our sources in case the existing methods were not working out. So that's the high-level overview and the high-level conclusion phase of our talk for today. I do want to open up the floor for questions. And if there are any high-level areas that we want to go back and address, especially in any of the labs that we went too fast in, or any of the parts of the section of the presentation that we didn't really go into depth, we can do that right now. since we have a lot of time, we have some time left actually to answer those questions for you.
Yeah, the first one is there's an OpenSHMEM. What is that? OpenSHMEM is an open source standard for a SHMEM-like programming library. So NVSHMEM is actually NVIDIA's implementation of OpenSHMEM, if that makes sense to you. Is OpenSHMEM actively developed? Yeah, there's an OpenSHMEM community and so on.
Right. As far as I remember, there is OpenSHMEM spec 1.5 or 1.6 or maybe even higher. But we were at some point based out of OpenSHMEM 1.5 spec.
I think 1.3.
1.3. Thank you for correcting me, Ben. Yes.
Yeah.
And so the APIs that NVSHMEM has, which don't have an X extension, are basically compliant to the OpenSHMEM standard. And there are other implementations of OpenSHMEM. Like there's a Cray implementation of OpenSHMEM. There is a Sandias OpenSHMEM implementation. There's an Intel SHMEM implementation, and etc.
I just sent the link to OpenSHMEM's GitHub org. They have the spec there. Yeah, exactly. As Pepper says, OpenSHMEM is a standard. It's a fixed set of interface and requirements. Is there a Python binding for NVSHMEM? Yes.
Yes.
That was lab 6.
6 for you. I brought it up on the screen in case there are any more questions about that. But yes, and there's also a Python binding for OpenSHMEM. It's called SHMEM for Pi. In fact, Jeff also
our colleague Jeff was one of the authors on that paper a couple years ago, as well as Lissandra, who worked on MPI for Pi.
Yeah.
Are other SHMEM implementations supported? Do you mean are other SHMEM implementations supported on NVIDIA GPUs? I don't think so, no. So NVSHMEM has NVIDIA GPU specific extensions.
Yep.
If you're asking, are other SHMEM implementations supported by CPUs? Yes. And you can actually use OpenSHMEM, OSHM run, and so on to launch and bootstrap NVSHMEM. That it's interoperable in that way. But you can't use the things that are NVSHMEM X, like NVSHMEM SHMEM extensions. You can't use those from other SHMEM implementations.
Yeah, now is a good time to. Okay,
is there a Python binding for nickel? There will be. That was on the roadmap slide. Where is nickel recommended versus NVSHMEM recommended? Yeah, so I think Arnav went over that in his slide 35.
Right. So I'll try to add some more color to that because I know that question has come up a few different times by a few different people, right? So NVSHMEM as historically, as you know, has been an implementation of OpenSHMEM, right? And so it's a specification, it's implementation of an OpenSHMEM specification, which is for the cluster of NVIDIA GPU, right? And as you know, the programming model describes a single global runtime and including its symmetric memory abstraction as well as the higher level abstraction that its API exposes. What I mean by the higher level abstraction is when you have APIs like when you have custom communication kernels which want to be able to not worry about the transport specific behavior and want a single interface to be able to say, I want to move the data as efficiently as you can, and the runtime should make the decision for me. Well, you have a higher level abstraction APIs that NVSHMEM provides through its device API, right? But with a higher level abstraction, you now have less degree of control, right? Which means now you may not be able to get the performance that you want to optimize, especially for certain Ninja users who may say, if I want to move data over NVLink, use exactly this specific API that you have, maybe just use the block variant only. Versus if I'm moving data over InfiniBand or Rocky or other RDMA transpose, use the thread API because I'm going to be using other threads to do other operations, right? And so you don't have a lot of flexibility and control in doing that, meaning you will have to make transport, either you have to make transport specific decisions in your code, or you are stuck with the decisions that NVSHMEM is making for you in those use cases. And a lot of users are okay with those decisions, and they're okay to write applications using that and get performance. But some users want to squeeze every single last bit the system can give you, right? Nickel, in its upcoming releases, also provides a device API abstraction. But what it is doing is these APIs are built from scratch, and they're built from scratch with the intention of operating on a communicator-based model. So Nickel, unlike NVSHMEM, operates on a COM abstraction, which essentially is a group of participating ranks. So that means the symmetric memory that you create is defined or associated through that to that communicator, and the association is obtained through something called a window-based abstraction, right? So this is different from the NVSHMEM malloc API, which allows you to have a single global runtime and just give you a symmetric memory buffer, but it requires all the ranks in your workload to participate in that abstraction. So you can see right there itself. One is a global runtime. One operates on global memory allocation based model, and one gives you transport agnostic APIs. But the other side is able.
Do you want to show the table while you're talking? It might help as a visual aid.
Yeah. While the other gives you the communicator-based abstraction, gives you symmetric memory, abstracted through the communicator, the means of a window. And last but not least, the device APIs that you will see in Nickel have been designed in such a way where user decides what kind of transport it wants to target. So if you want to move data over NVLink, you have an API that just moves data over NVLink. You want to move data over InfiniBand or Rocky or some sort of RDMA transport, you have an API just to do that. We don't hide that abstraction away from the user. We let user take full control. So for users who want more lower level abstractions and they want to have transport specific code in their kernel, which we realize a lot of the custom communication kernel authors want to be able to do that, we offer that in Nickel, right? So given the fact that you have all of these capabilities and you have different kind of audience, you have kernel authors who want to write custom kernels, you have framework developers who want to use Nickel and NVSHMEM in different ways, and you have application users who may want to mix the two, like you guys were asking about earlier. We give the audience, or we give the users or the community the control to pick and choose what library makes most sense based on the programming model of their application, the level of abstraction that the kernels can operate on, and the type of device APIs they want to use, right? And that's why it's a choice completely driven by the community, and rather than a choice that we are making for the community. And that's a good way to think about how you want to mix and match the two in your use case, or you may just want to use one over the other because you have a completely different programming model.
Yeah, thank you for that. There's a few other ones here. So are Nickel and NVSHMEM used with std_par? They can be. Their std_par builds on top of, uses CUDA, and you can certainly interoperate NVSHMEM and Nickel with that if you want to go multi-GPU. Why is it called symmetric memory? It's called symmetric because it looks the same to everybody. So same chunk sizes, same offsets for every PE or rank. That's why it's called symmetric. Symmetric meaning same.
This is a good way to think about symmetric memory, is that you have the identical offset across all participant rank, and you have the same size being used by all of the participants.
Yeah, and thank you to Tony. You get a special shout out. Strictly speaking, it doesn't have to be the same address, but all the addresses must be translatable. That's true. So follow-up question, how is the latency difference between local HBM and remote HBM access handled? That is sort of part of the point of having an explicit put get is being able for the application to manage that.
So I didn't quite hear that question, Ben. Could you repeat
the question is how there's a latency difference between local HBM and remote HBM, right? So when something's on the symmetric heap, if you're looking it up from someone else, you should assume that you're going to get the remote HBM latency, right? Unless you're doing something very special where you're doing a specific type of identity lookup where you're always going to be going to yourself. But basically, it's application managed is the answer.
Yeah. You are in control. I mean, the symmetric memory pointer that you get is the pointer to your own piece of memory, right? So that's the pointer that you can basically pass into CUDA memcopy or any other CUDA API because it's basically a pointer to your own local GPU memory. Now, if you want to get the pointer to the remote GPU memory and from your application, there's an API in NVSHMEM called NVSHMEM pointer. It's a query method. You can give the symmetric pointer the rank you want to target, and it'll give you the virtual address for the peer memory. Now, why is it a virtual address? It's because when we create the symmetric memory, we're basically memory mapping the peer's GPU memory into our own address space. So now we have a virtual address space that is associated to a local memory on the GPU, and we have a virtual address space associated to the peer memory on a remote GPU. And so we can give you a view to that through the NVSHMEM pointer API. And then you are in control to say, okay, if I'm doing an access to local, I can just use the output returned by malloc, NVSHMEM malloc. And if I want to use the pointer to remote and do some sort of load store operation, I can just use the pointer returned by NVSHMEM pointer. So that's the level of control that the application has, and that's the part that Ben was talking about earlier.
Right. Yeah. So okay. So yes. So thank you, Arnav, for clarifying that. I was saying, what I was trying to say is when you're using operations like put and get, or when you're operating on something that you got from NVSHMEM pointer, you should think of that as having a high cost of access. And thank you, Arnav, for clarifying. We have a follow-up question. What is the latency difference? Is it about nanoseconds versus microseconds? I'm not going to go into the specific details of number of nanoseconds and cycles that everything takes because it really depends on your hardware. But basically, if it's a local HBM lookup, think of it like DRAM, right? So it's a local memory lookup. You can think about that like any other DRAM attached to your chip that you're working with. And if it's not local, then it's going over some kind of a fabric, whether it's NVLink or PCI Express or network. And so it's going to take much longer. But I can't answer that question specifically just because it really depends on your hardware and your system.
And there's a question about symmetric memory being shared or replicated. I'll clarify. So if you're familiar with the database concept of replication, it's different here, right? So what's happening here is that every GPU allocates its local private memory, which is happening as part of the NVSHMEM malloc call. And so now every process knows, once it's allocated its local memory, what is the virtual address for that memory. Additionally, you create what's called a symmetric address space, which manages both the local as well as the peer accesses, right? So what I mean by peer accesses is that every GPU that's allocated its local memory would now have to exchange that memory abstraction between these processes. And CUDA has a way to do this. It's called CUDA IPC. So you can create it on local memory objects. You can exchange the two between the processes. And then you can now map a peer GPU's memory into your own virtual address space. So what you have is not a copy, but a view. View by view, you mean you have a virtual address. So when you issue that virtual address from within the GPU kernel, the GPU knows that this is now targeting an address which is actually addressable by my NVLink fabric. And so the transaction, the packet will go over NVLink. And then on the pure GPU side, this particular transaction would hit the remote HBM memory. So all of that abstraction of how the address translations, how the view is created, is hidden behind the covers through NVSHMEM malloc. What you have is a zero-copy way of being able to access a peer GPU's memory by directly loading and storing from it. You don't replicate the physical memory on the peer side into your local side. You're only making a larger virtual address space for you to view into the peer GPU's memory. Does NVSHMEM support MIG? How about MPS? I think Ben has already answered that. Yes, it comes with.
So MPS, yes, with some restrictions. MIG, I don't think we support MIG, do we?
No, we don't support.
Yeah, we don't support MIG.
In NVSHMEM, we support something called MPG, multiple processes per GPU. That means multiple processes can essentially share the same GPU. However, there are some collectives and some APIs that we don't support in that paradigm because it would lead to some sort of deadlock conditions if we try to do that. And you can think of it more like the use cases that a lot of the NVSHMEM kernels or the Nickel kernels try to build for is single programming multiple data, where you have one process use one GPU in the most common use case. and build applications around that. But we have support for some of these MPG and MPS use cases in Nickel and NVSHMEM, and we have restrictions and limitations around that. And I think our API guides are the right source of truth on that. Okay, I think I covered some of the questions that were asked earlier about, the two libraries, its capabilities, and the similarities and differences. So we have about 15 minutes before the end of our presentation. Are there any more questions or any more areas or any more labs that specifically need help? I did see a question about one of the labs where one of the participants was not able to make it work. Okay, I see that Ben has already responded. Okay, thank you, Ben. Do any operation on the remote memory have to be loaded into local registers? Yes. I mean, when you are loading data from the remote memory, the intermediate resources you have in the SM are registers and shared memory. So you have operation that would load data from even the local memory or remote memory into registers or shared memory. They're not necessarily um, to think of it differently. You can use registers and shared memory as one of the intermediates to store that data if you're loading it from any location, but that location does not necessarily need to be remote. It can also be local. So you can do a load from your local GPU's memory into a register. You can do a load from peer GPU's memory into a register. So the latency characteristics and the bandwidth characteristics of that would be different. Are MPI offload and Nickel comparable in terms of functionality? If so, how does the performance compare? That's a good question. My suggestion for that particular question is I don't think I will be able to do full justice by giving you a performance analysis on it. I do believe this is an area that Jeff's talk actually covers very well in detail. So Jeff actually kind of walks you through an all-to-all example built with MPI, OpenSHMEM, Nickel, and NVSHMEM. And there's a performance comparison of how all of those different libraries support the different ways of doing all-to-all and how they perform for different use cases. So my suggestion is, watch Jeff's talk. It would do good justice to do the comparison between the two. There are comparable functionalities between Nickel and MPI. Put in a simple way, MPI also supports GPU memory buffers in some cases. So it internally would copy from CPU to GPU depending on some protocols, or it would use GPU direct RDMA to move data from GPU to GPU without staging it on the CPU. But those protocol choices, those design decisions are purely an MPI library decision, and rather than talking about what MPI can and cannot do, I would highly recommend you to review Jeff's talk because he's an expert in that area and he does justice to providing an explanation around that too. Nickel does borrow some of the concepts from MPI, like a concept of a communicator, but the communicator is built using a set of ranks and size that the user decides. It's not something that's global to what the launcher decides for you. So there are differences you can see right there itself in how the communicator abstractions are used.
Yeah, and Jeff has been involved with the MPI forum for like 2 decades plus, so he really knows that stuff.
I do want to bring up that for Nickel 2.28, the GitHub preview is live. You can take a look at it, try a few features. We'll have a blog post about how to use these features in near future.
Yeah.
Can NVSHMEM operations be put on a CUDA graph? Absolutely. So actually, some of our testing uses CUDA graphs. So yes.
Yes, that is supported. You can write a CUDA graph capture instantiate. You can make a CUDA graph. You can write a stream capture, put your operations on the stream, and then you can end the capture, and then you can launch that graph. And in fact, there should be examples already in NVSHMEM repo that provide you a way to do that. So you can try that. I think Ben or Pouya can put the link to that example here if it's not already shared.
Is there an example on the website, or do you have to download the source tarball?
I think it'll download the source tarball.
Yeah, so I don't think we can put a link, but if you go and log into the NVIDIA Dev Zone, you can download the NVSHMEM tarball, and there are examples in there.
All right. Since I'm assuming that there are no more questions about the labs
There are
specifically.
people typing.
Oh, it's still typing?
okay.
Okay.
How
How
can
can
one
one-
make suggestions to improve the docs? So go to the NVSHMEM. For NVSHMEM, go to the dev forum. And for Nickel, go to Nickel GitHub. Those are the
Very
best
soon when
ones.
we'll be having NVSHMEM GitHub as well, you should be able to also give us suggestions there too. But in general, if you have something that you want to point out, you can put it on that thread and we can try to see if there's anything that we can help you or alleviate that or help the community in general.
Yeah. And yeah.
Which
Each
components maintain the global logical view of the remote HBM for the mapping?
Which component maintains the global logical view for the remote HBM or mapping? So that would be CUDA. CUDA provides a way to maintain mappings for accessing memory of a peer GPU over NVLink. NVSHMEM is a user of CUDA, so it builds on top of the CUDA APIs. You can take a look at the CUDA virtual memory management interface. It has APIs to allocate memory, allocate physical memory, allocate virtual memory, map them, as well as export or import them between processes. And that would be an abstraction that NVSHMEM builds around. Also, the NVSHMEM code base is available for you to download and view. So you would want to then go look at how NVSHMEM manages a symmetric heap using the CUDA APIs.
Yeah, these are some of these questions are like inherently like Nickel and NVSHMEM. So while like some other libraries use their of their like memory handling like as part of their library stack, like we depend on CUDA to do this.
Yeah. CUDA has some really fancy memory management features.
Okay, if there are no more questions, I think we can conclude. If you are still facing issues for the labs, you can Slack us. I think it's active till tomorrow.
Yeah, the Slack is active till tomorrow. We really thank you guys for your time for today. And if you have any more questions, we can stick around for a few minutes on Slack and try to answer them. But we really appreciate everyone kind of joining in for this talk. We hope this talk was useful. If there are any labs that don't make much sense or that you guys still have questions for, we have time until tomorrow to leave them on the Slack, and we'll try to make sure that if we get an opportunity to share the code, we'll check with the hot eye team on that. If we get an opportunity to share the code, then we will address those questions hopefully through READMEs to make them more as expressive as possible.
We will after that go to the dev forum. There's an NVSHMEM tag, and go to Nickel GitHub, and I think there's a Nickel tag in the dev forum as well. And the maintainers, the project developers actually like look at those places, so you will get engagement. How long can we use Jules Booster? I think after today it goes away.
Yeah, I think Andreas just answered.
Yeah, he says a few hours, so use it while you can. It's a really nice system. And thank you to Andreas and JSC for providing these resources. This is like you guys are getting access to some really nice GPU hardware. So thank you very much for that.
We're happy to support this endeavor.
Yeah, thank you, Andreas and team. This was really great. Yeah, we're getting a lot of feedback from users, so enjoy the tutorial. We're really happy for that. Yep, I'll stop sharing my screen for now. All right, I think Jackson, back over to you.
Yeah, thank you.
All right. Yes, thank you to our presenters. And I also wanted to mention that the recording will be available later on the Hot Eye YouTube channel. So, yeah, thank you very much.
Thank you.
Thank you.